Hi class, we are on now chapter 7.8. This is involving relationships and enthalpies. Enthalpies in chemical reactions generally are measured with calorimetry using the standard, the Q equals MC delta T, can be reported in units of kilojoules per mole of reactant used or product produced, and most often given after a chemical reaction, indicating the enthalpy change associated with the reaction stoichiometric amounts of reactant used and products produced. That's the coefficients. Those are just the values that go with it, and the coefficients, and that equal. The coefficients are specific for that value that you see. So an enthalpy change is equal to the heat transfer for a process carried out in constant pressure. This is just a little bit review. Change in enthalpy is a state function. We only care about the beginning and the end. Change in enthalpy depends only on what reactants and products are, and not particular chemical reactions that were carried out to get from one to the other. So again, we don't care about the middle. And a change in the enthalpy of reaction is the enthalpy change for a specific chemical reaction occurring in stoichiometric quantities. That means exactly the coefficients and the values for that. They have to if anything's changed, they have to be adjusted. So here's a perfect example. This is from another slide that you've hopefully have seen before. Delta H, the reaction is extensive. That means that it is the mass that you have. If you add more mass, then you also have to adjust the change in enthalpy for it. So the mass is basically determining the values that you see. In this case, you can see where we had carbon and oxygen, and when it's produces carbon dioxide, this is specific value for this coefficients. And if you double that, you also have to double the change in enthalpy value. And if it's reversed, you have to change the sign as well. So everything has to be adjusted if there's a change of any type. So let's go through and make sure you guys understand how to do this. Water can be formed via the reaction of gases hydrogen and oxygen. Write the balanced equation that shows 1 mole of water produced. So up here we have 2 moles of hydrogen, 1 mole of oxygen, and then 2 moles of water, and this is the value that it gives. But we want 1 mole. So how do you do 1 mole? Well, you simply divide everything by half, everything. So now we have 1 mole, we have half, and in this case we can use halves. That's perfectly fine. And then 1 water. And in the process of that, where this is only asking for the balanced equation, the second half is asking for the enthalpy reaction. So in this case, we take the value that we see here divided by 2 moles of water, because it's asking for determine the enthalpy of the reaction in units of kilojoules of moles for the water produced. So here's for the water. Remember, these are conversion equalities. And then we are going to divide everything. So this value will be divided, and that means that this will be for 1 mole of water produced. All right, so let's look at the equation and enthalpy for combustion of methane as it's followed. So here's an equation. We have the change in enthalpy value. Determine the amount of heat produced by the combustion of 3.30 moles of methane. So we're not even looking at B yet. We're just looking at A. So remember, this is a conversion factor. Anything that you see here is equivalent to this. So what is it asking? It's asking for methane. So we're going to look here. So that means that 1 mole of methane is equivalent to negative 891 kilojoules. So that's kilojoules per mole because this is 1 mole. So we set that up. We take the value that's given. We use that as an equality. And this gives us a value of 2,940 kilojoules. Now, it's asking, this one, it makes sense and it doesn't make sense. It's asking for the amount of heat produced. So the amount of heat produced is negative. I would have left this with a negative, but technically it is correct because it's only asking for a value. It's not asking for more than that. So I would give it either way on this, but I would like to be consistent. I think I would leave it with the negative value on it. Okay, determine the enthalpy for the equation. So in this case, if it's multiplied, everything here's been doubled. You can see here's the original. Here is it being doubled, which means that you also have to double the value. So if we double the value, it is negative 1780 kilojoules. Okay, so Hess's law. The enthalpy changes for some reactions are difficult to measure directly. We just can't. So these can be calculated by manipulating other equations. Now this is something that you should have covered in Chem 111, so this is pretty much review and hopefully it's coming back to you. So we can use other equations, and then through the process of adjusting or editing, we can figure out the enthalpy change value for the reaction that we're interested in. So when chemical equations are added together to yield a different equation, the corresponding values are added to get the desired equation. So they're added together, but we sometimes have to adjust that. This is called Hess's law. So pretty much what it is that we can take the overall reaction, the sum of the heats of reaction for each step. So this Hess's law is that we can take these reactions, and through the sum of these steps of these, we can add it together, and we can get the value for what we want for our desired reaction. So that's all this is. This is just a fancy way of showing that if we do one reaction, we add one equation together with another equation, we can therefore get to our desired equation. But of course, there's editing and adjusting to those equations. So using Hess's law, if a chemical equation is multiplied by some factor, then everything needs to be multiplied by that factor, including the enthalpy change of enthalpy for the reaction. If a chemical equation is reversed, then the value also has to be reversed. If a chemical equation can be expressed as a series of steps, then the change in enthalpy of the reaction for the overall equation is also the sum of all of those reactions, heats of reaction for each step. So I've got examples if this isn't exactly making sense. So rule number 1, there's 3 rules that have to be followed. When an equation is reversed, the sign of the enthalpy also changes. So if we see here that we have it's a positive value, and we start with nitrogen gas and oxygen gas. But if we reverse it to a decomposition reaction, we also have to reverse the sign. Next one, when coefficients in the equation are multiplied or divided by a factor, that means the enthalpy value is also multiplied or divided by the exact same factor. So here we have calcium, we have oxygen, but we have a coefficient of half. And then we have calcium oxide, and it's giving a value of negative 635.1, but here we have everything doubled. So there's a 2, you can see that this is now a whole. That means you also have to double the value. So whatever factor you use, you have to use it straight across on everything. When excuse me, my cat's meowing. When reactions are summed, the enthalpy of the overall reaction is the sum of the enthalpies of the component reaction. So this is basically stating that you have to add everything together in order to get the overall total as the value as well. So here you can see that we have carbon that's made out of diamond, and we have oxygen, and it produces carbon dioxide and gives this value. We have this value here that is carbon dioxide. It decomposes to carbon and oxygen, and it gives this value here. We have to add them together. Because we're adding these together and everything cancels out, that's not being used, because if it's on both sides, it's like a spectator ion. It's not doing anything in this. We add this together, we also add this together. The values have to be added together, the reactions have to be added together. So here, let's do some practice. We have an equation that we do not have a value for, and we need to get a value. So we have carbon as a solid, we have a coefficient of half for oxygen gas that produces carbon monoxide, but we don't have the value for this. So we're going to take 2 reactions, and the first one looks very similar to the one that we need to solve for, but if you see, it's carbon dioxide, not carbon monoxide, but we have a value for that. Second one, we have carbon monoxide, but this is another step that produces carbon dioxide, but it's not carbon. So we're going to use both of these and kind of adjust and edit them in order to get the equation that we want listed in blue. So reaction 2 must be reversed to put CO on the product side, and the sign will have to be changed as well. So we'll have to reverse what the sign is because we're reversing the equation. Then adding reaction 1 to the reverse reaction 2 will produce the desired chemical reaction. So let's take a look at that. We have the reverse reaction, we have the reaction 1, and everything should cancel out. So we have carbon dioxide on this side, carbon dioxide on this side. We have one mole of oxygen here. We have half a mole. So basically what this is 1 minus half equals half, which is what we see here. And then we can bring all of that down in an overall. And then all the steps that we did, we have to add together. and which is done here. So the delta H for this is negative 110 kilojoules. And then this is just a fancy diagram showing overall what we did, the steps that were taken to get to our value. Okay, so here we use the delta H values for equations 1 and 2 to calculate delta H for the vaporization of ethanol. So we have, this is the same compound, however, it's going from liquid to a gas, and we have two equations in order to get that. But we have different compounds that are also part of this equation. So we're going to need to edit this in order to get to the value we want and to have the equation look like this. So to achieve the needed equation, we need to first reverse equation 2 and then add it to 1 and then cancel the terms. I forgot to put the things to cancel. Oh no, it's then. So here we have equation 1. It was here, it looks the same, but equation 2 was negative and now it's positive. And now, if you were to bring down every single part, you would see that there are reactants and products that are matching that have nothing to do with the actual equation. So we basically did some house cleaning and removed them. And now we have our equation again that's been given to us. And we also have the values that we need to add together. And the value of this is a positive 42.6 kilojoules. And that's it.